Hey everybody. I think I'm going to start doing lectures where it's only one section per video. So we're going to start today with our lecture 3, part 1, which is going to be section 2.2. Now we're going to get sort of into the nitty-gritty of the class, because what we're going to be doing from here on in really is figuring out all the different possible methods for solving differential equations, because differential equations come in all kinds of shapes and sizes, and each different kind of equation may need a whole different method for a solution. So as we go along, we'll sort of see what these classes of equations are. And it might seem at first like we're just pulling out methods, but what's true is that you'll get to know the classes, the kinds of ordinary differential equations. We won't get to partial differential equations till the very end, but you'll get to know those kinds and get a feel for what method you need to sort of pull out of the box to solve for that particular equation. Okay, so let's start. So what we're going to do is start with the simplest kind of differential equation, and that is a first order. So here we're going to write the simplest kind. And I apologize for any spelling mistakes. That's not my thing. Okay, of differential equation, and that is first order. You know what that means? It only has the highest derivative it has is the first derivative. First order and separable. So I'm going to define what that means in a second. These are the best kind. Now, it doesn't mean that you're going to get to a solution always, and you'll see that too. But you can get the form of the solution where you might need to do a numerical integral or something, because your integral, you can't integrate it. And you may have an implicit solution. We talked about those before, where you can't solve for y. So it's not like you could, it's perfect, but you can get the form, and that can allow you to do a lot of things. Okay, but we'll see plenty of examples of the easy stuff first. Okay. All right, so our simple equation looks like this in general. Well, actually, let's do an example first, but I'm going to be a little bit abstract. So I'm going to say, let's look at an equation that looks like this. We're going to put it in its normal form. dy dx is equal to a function of x. Pretty darn simple. I'm not even letting it be, there's no function of y over here or anything yet, right? So I'm just super simple, the simplest possible thing. Okay, so we're going to assume that g is continuous. Now, there are differential equations in which g can be not continuous, and you would have to sort of solve it in piecewise manner, and we might get to that, but let's just assume it's continuous. So we're going to make the assume g doesn't have any breaks, continuous. Okay, all right. Now, I want you to notice something. Now, what if I multiplied both sides by dx, right? I would have just dy over here. We did something like that before when we looked at the normal form or the differential form of equations. So why don't we do that? So we're going to multiply by dx. And you're going to see what I call it separable in a second. So that would just give me dy on one side, and it would give me g of x dx on the other. Well, look at that. I bet I could integrate both sides, right? So I could take an integral here, an integral here, and this would just be y on one side, and this would be that integral of g of x, whatever g of x happens to be. And I'm going to give you an example straight up here in a second. And we have some constant of integration, which I usually associate with this one, right? Again, both of these, because they're indefinite, would have constants of integration, as you well know. But I can just group them into one. And you're going to see that it's often a good idea to find the best form for your constant. Instead of having two here, it's much nicer just to group them into one, okay? Anyway, and I put it on this side because I think it looks nicer. All right, let's do an example right away. So let's do dy dx is equal to 1 plus e to the 2x. So notice this is only a function of x, okay? Certainly continuous. There's nothing about this that looks discontinuous, right? It doesn't blow up. It's not singular anywhere. It's not going to, there's no breaks, right? So it looks good. And again, you're going to assume that pretty much unless told otherwise. Okay. All right. Well, let's multiply both sides. So this is our, another sort of a real example in the sense that we're using the known functions here. All right. So we're going to multiply by dx. And we're going to get dy on one side, and we're going to get 1 plus e to the x dx. On the other side, again, we can integrate both sides, indefinite integrals. We get y over here, right? And we get x. Okay, the first term gives you x. Oh, I forgot my 2. What happened to my 2? Disappeared. The first term gives you x. The second term, of course, gives you 1/2 e to the 2x. I'm assuming you guys remember how to integrate things like this. And then we have our constant, right? So look, I have the solution, right? This is a family of solutions for y as a function of x, right? So I shall put the x in there. There we go. Right? Y as a function of x is x plus 1/2 e to the 2x plus c. So this gives me a family. And if I had an initial value problem, say someone told me what y at x equals 0 was, I could find out what c was, right? Cool. So this is a great method because it's so easy. Now, as you're going to see as we move forward, maybe this integral not so easy, right? In fact, you might even have a situation in which you can't do that integral at all without using a computer. But anyway, it's still a solution, okay? All right. Now, this is the simplest one where we didn't have any y's over here, right? We just have x's, so a function of x. Well, what if there is also a function of y over here? Well, there's still a special condition, and it's very often true for equations, where you can still separate and move forward. Okay, so let's take a look at that. So we want separable. What is the separable? Separable, there we go. Condition if we have y on the other side. Well, it has to look like this. Your equation, dy dx, has to be able to be written as g of x times h of y. So in other words, you have to be able to write your equation such that you have a function of x times a function of y. Otherwise, it's not separable. So for instance, if you look at an equation like this, let's look at this guy here, dy dx is equal to y squared x e to the 3x plus 4y. You might look at that and be like, oh no, I can't, that's mixed up, right? There's x's and y's over here, etc. But this actually is separable. You just got to write it in a better form so you can see that. So I'm just going to collect everything. I have x, and I can split my exponential, e to the 3x, and then I have y squared, e to the 4y, right? So now this is my h of y, and this is my g of x. Okay, well, how would we move forward in solving that? Well, what would we do? We can multiply by dx on both sides, like we did before. So we get dy is equal to x e to the 3x y squared e to the 4y dx. Well, I'm not quite ready to integrate both sides, right? Because I still have y's over here. But what I can do is take all of those y's, all the function of y, this is our h of y, right? And I can move it over to this side so that there's only y's over here and there's only x's over here. So let's do that. So we have dy, and then I'm dividing now by y squared e to the 4y. And then on this side now I have x e to the 3x dx. Now I absolutely can integrate both sides, right? All right, so if I integrate both sides, Now, assuming I can look up those integrals, right, or figure out how to do them, I can get an answer for this, right? Maybe maybe I have to do them numerically. I don't know. I'd have to go look up these things, right? Um, and you can, but you can get a solution, right? Because this equation is separable. And we'll do some examples that actually can be done. Okay. Here's one. So let's look at this one. We have dy dx is y, oops, sorry, y over 1 plus x. Oh boy, I'm messing this up. Just a second, let me get my brushes. Eraser. Okay, goodbye. I think I was on the ballpoint pen. There we go. Okay, messing that up. All right, we're gonna have y over 1 plus x. Okay, well, what is h of y here? It's just y. What's of g of x? It's 1 over 1 plus x. So let's separate, okay? So I'm going to kind of skip a couple steps now that you've seen the separation process a few times. All right, I'm going to take the y and put it underneath the dy, right? So I just moved it over to the other side, and then I'm collecting all my terms, and then I have a dx over the 1 plus x, okay? Now, we could integrate these two sides pretty easily, because this is, you know, the ln of y, and this is the ln of 1 plus x, right? To change variables to get that, but hopefully you can convince yourself that that's the case. And so what do we get? We get ln of y on one side, and we get ln of 1 plus x plus c on the other side, right? Okay, now here's where I want to sort of point out that where you put that constant of integration, how you formulate it, what form you put it in, can really make all the difference. So if we now let's let this c, right, we're going to put it, so we have it on this side, that's fine, but let's make it into an ln. So I'm going to define this guy as ln of d, okay? Fine. So now, there's no reason I can't do that, right? I mean, if I knew this c was 3, right, I would just redefine d such that this was e to the c, right? So there's no reason that you can't change the form of these constants. So now I have this as ln 1 plus x plus ln of d, and you're going to see why this is convenient, because I'm now going to take the exponential of both sides to get rid of these ln's. Okay, so if I take the exponential of both sides, on one side here I'm just going to get y, which is what we want. On this side I get e to the ln of 1 plus x plus ln of d. But what it can do is separate that out, right? I get e to the ln of 1 plus x, so that's just 1 plus x, and times e to the ln of d. So I'm going to write that first, e to the ln of d, and then I get 1 plus x. Okay, but this thing here, e to the ln of d, is just some other constant. I don't know, call it f, right? Okay. Do you see how that works? So now this is in a nicer, kind of a nicer form than before, right? Than keeping it sitting out here. Often this is, you know, just makes it easier for you to implement the initial value or whatever, right? But you see how the separation works. Okay, let's solve an initial value problem. Get another layer here. Oops, no, there we go. Okay, so let's solve an initial value problem. Again, we are on section 2.2. All right, here's our differential equation. dp dt is equal to k p, where k is equal to 0.01 per year. This is now the population equation, and this is the rate of population growth. Well, the proportionality constant for population growth. All right, And we have an initial value that we want as p at t equals 0 is 1,000. So there's 1,000 people originally, okay? All right, because this p is the number of people, right, the population. All right, so how do we solve this? Well, it's very simply separable, as you can probably see. So let's take dp over p, and then on the other side we have kt. I'm not going to put in the numerical value till we evaluate it at the end. Anyway, dt, right? And now I can integrate both sides again. And I get ln of p on one side, and then I get, did I do this wrong, dt? Oh, yeah, I totally did. Okay, this is just k, not kt. I haven't integrated it yet. And on the other side, I get kt, and then I have the option of just saying, hey, I'm going to call this ln of c, the constant, right? And that's because I have an ln on this side, and I'm going to have to exponentiate. So why not just leave it like this? Okay. Okay, so actually, let's go back to that other layer for a second. We'll turn this off. I just want to point something out because I think I wasn't too good at that. So if you look at this, e to the ln of d would have given me d. So I didn't really need, right? I didn't really need to make this a new constant f. I could have just said, hey, that's d, right? Just FYI. I tend to overdefine my constants here, but right, because e to the ln of d just gets rid of the ln's and you get d. And just pointing that out, that's kind of silly. All right, let's go back. Okay, so now, if I take the exponential of both sides, right, we get p of t is equal to e to the kt times e to the ln of c, which I can just write as c e to the kt. Okay, so now I know how the population changes with time. And as you can see, it exponentially rises because k is a positive number. Okay, so let's just implement our initial value now. So at p at 0 is supposed to be 1,000. And if we look at p over here at 0, it's just c. So that tells me that c better be 1,000. So my final answer for the initial value problem is p of t equals 1,000. And that's in units of people, right? E to the kt, and that's 0.01 t per year. So we would want t in years. So just as an example, if we say, let's let t be 20 years, right? And we plug in numbers, I think I got something like p at t equals 20 is going to be 1,221. So 221 people were born with this particular constant, right? Okay, anyway, that's how that works. This is a very common equation, the equation where you have something like an ln of something on one side and then some dependence on time on the other side. Very common. You'll see it all over the place, right? We see it in quantum mechanics classes. We see it in atomic decay equations, etc. Okay. Now, one thing is just to be careful about is that, you know, if you notice here, I divided by p, right, here. You have to be careful when you're dividing through. So very often you're dividing on maybe even on both sides by some function of x or t or y. You know, if you have an equation that's of this form, or separable equation like this, you know, you may divide, if you divide by if you divide by h of y over here, right, that h of y might have zeros, and then your solution, you have to be careful about your solution. So there's really not a whole lot you can do about it. You may actually have to drop that solution, the solution where the zeros are. So if you have so let's just separate this guy. So we have h of y on this side, and we have g of x dx. This is undefined at the zeros of h, right? So if h has a 0, then it's kind of undefined. So if we let r be a 0 of h, right, Um, then when you have y equals r, right, you have dy dx is equal to 0 because r is just a number, and you have the right side, the bottom is 0 as well, or the right side is 0, right, if you wrote it in this form. So this is sort of a stationary point, a constant solution. But what's going to happen when you actually do the separation is you're going to have to sort of drop this solution in your calculation. And we're not really going to use that, but I'm just letting you, making you aware that if you have zeros in that equation, that you may be actually losing a solution, and that solution will be the one where where h has zeros, or the multiple possible ones where they have zeros. If h is some polynomial, you might have multiple zeros, etc. We're not really going to harp on that point too much, just making you aware of it. Okay, let's do another example. And now here is where we're going to see an explicit solution. Okay. All right, how about this differential equation? We have e to the 2y minus y cosine times the cosine of x times dy dx is equal to e to the y sine of 2x. Right? So this is certainly separable if you notice, right? I could take this, leave this here on this side, move this over to the other side, move this over to this side, and I'm good, right? So, totally separable. So let's write that out. It's not simple, but it is separable. Okay, over e to the y on this side, and I have my dy, and then I have sine of 2x on this side and cosine of x over here with my dx. I could integrate both sides, and to get the answers for this integral, you basically do some manipulation and then look them up, right? This isn't a calculus class where you need to whip out every possible way of doing integration. So don't worry about having to, do these integrals. Remember how all the different methods for doing integrals. All right, so I'm just going to write down the answer. So the answer is e to the y plus y e to the minus y plus e to the minus y is equal to minus 2 cosine of x plus c. So this is our family of solutions. And if we say that we also are making this an initial value problem where y of 0 is 0, right? And then so if we put y of 0 in here, right? So we get a 1 here. This goes away. You get another 1. So you get 2. And then you get a minus 2, which would be a 4. So you basically end up with c equals 4. Prove that to yourself. I'm going a little quickly. So your final answer here, which is pretty ugly still, e to the minus y here plus e to the minus y equals 4 minus 2 cosine of x is an implicit solution, right? That meaning that it's not y equals something. It's some function of y is equal to some function of x. Y is not by itself, and it's really difficult to, if not impossible, to solve this for y. Right? Very often we call equations like this where you can't solve for one of the variables, they're also called transcendental equations. Kind of a fancy name. Okay, so this is the best you can do, right? You can't get y equals something. So don't freak out if you get something like this. Make sure that you try to solve for y. Well, you don't try too hard, because if you tried on this one very, very quickly, you would get yourself in trouble and not be able to move forward. and it's fine to have an implicit solution. Yeah, it's not as nice, it's, to use, but it's certainly fine. Okay. Now, what if you just can't integrate, right? Because this whole thing depends on being able to integrate stuff, right? Well, what if we can't integrate? If the integrals are too hard? Well, you could, of course, there's a couple things you can do, right? You can, one, use a computer. To numerically integrate. That's an N. Okay, sure. But you can actually define an integral equation, and that's what we're going to look at next, because it's often nice to have the thing in that form. Let me get another layer. Okay, so this is again the case where we really can't integrate, and this is section 2.2. All right, so let's look at the equation. Dy dx is equal to e to the minus x squared, and with an initial value y at 3 equals 5. All right, let's separate. Certainly separable, no problem. So we have dy is equal to e to the minus x squared dx, and we can integrate both sides, right? This side, that's easy. We get y, right? And then on the other side, we're like, uh-oh, right? This thing actually does not have a closed form for an indefinite integral. It looks pretty easy, doesn't it? It's just e to the minus x squared, but it doesn't have a closed form. So what do you do? Well, there is a way of writing this that kind of does the most you can do before you get stuck. Okay, so let's look at that. So let's back up a little. So we're going to go back to dy is equal to e to the minus x squared dx. And what we're going to do is we're going to take our dy, we're going to divide and multiply by dt. Then dt is just sort of a dummy variable that's being used. It doesn't necessarily mean time at all. It's just a dummy variable. I could have used y prime, but that just gets confusing. So do that on that side. Notice I'm just multiplying by 1. And over here, I'm going to do something different, but let me continue. So remember, what we want to do is integrate. So I'm going to integrate this, and I know what my initial value should be, right? So at x equals 3, I'm going to integrate from there to a value of x, okay? And you're going to see why we do that in a second. But on the other side, I'm going to do the same thing. I'm going to integrate both sides in exactly the same way. I'm going to integrate from 3 to x, and that means I better use kind of the dummy variable over here. Again, I could have used like x prime, right? dt, but t is just easier to see in what you're doing. All right, now this guy here, if you notice, is just going to be y of t evaluated at 3 and x, right? Kind of cancel that out, and then you use fundamental theorem of calculus. And that, if I write that out, is going to be y of x minus y of 3, right? Well, I know y of 3 is 5, but I'm not putting it in there yet. But I used it because I want to be able to put it in there later. Okay, so that's one side. So on this side, there's kind of nothing I can do with this side, right? It kind of just sits there for a second. All right, so we'll leave it. So we have on this side, we have y of x plus minus 3. So y of x minus y of 3. Sorry, I meant y of 3, and that's equal to this integral formulation 3 to x e to the minus t squared dt. Okay, so now I can actually solve for y equals y of 3 plus the integral from 3 to x of e to the minus t squared dt. Okay, and this y of 3 is 5, so I can put 5 plus the integral 3 to x e to the minus t squared dt. Sorry, this is bad. That looks like it's in the exponent. dt, right? And this is really kind of the best you can do when you have an integral that does not have a closed form. And if this one, no matter what you try to do to look it up, it's not going to have a closed form. Now again, you could numerically integrate it, sure. But this is the second thing you can do now, right? The just leaving it in this form, this sort of integral equation form. Okay, so that's all we're going to cover for section 2.2, and the next part of the lecture will be section 2.3. But a good thing to do is watch the lecture. Maybe you might have to go back and figure out what things you didn't understand. Then read the book, and you'll see that the book may go into a little more detail here and there. That's fine. And if you get confused by that detail, take the lecture as your guide. And then what I would do is I would go to the homework system for this section. The homework problems are, for homework for chapter 2, are labeled by section, right? So I should have told you to do this when we started, but my technique, if I were you, would be to do section by section, go do the homework, right? For that section, there'll be 2 problems per section. So do those problems. And if you have time, and I know this class is quick, I would be doing more problems, all right? There are, in the book, there are problems with answers, so you can check yourself, all right? So you can go to chapter 2.2 and go to the exercises and do more problems. I mean, that's what I would do. I realize that you have limited time, but math and physics are all about practice, okay? And you wouldn't practice violin for a minute and expect to get anywhere, all right? So try to spend more time. It's a rigorous class because of the short time, so do your best. Okay, well, we'll see you next time for section 2.3.